Okay, this is the third and final video for running through the Advanced Higher Prelim. I am not recording this first thing in the morning, but I have been teaching all day, so my voice is a bit rubbish again, so apologies for that. This is obviously the remainder of section 2, this is week 2. And again, it's just a mixed bag of all 3 units. This is near enough a full course prelim, with some content from unit 1 missing, because we've not covered that yet. So that maybe has added to the reason why, particularly in week 1, the unit 1 content maybe felt a bit trickier, because there's more coverage of unit 1 content that we have covered just to make up the numbers and make it fairer. Whereas obviously we had a bit more to play around with from unit 2 and unit 3. So it maybe felt like not as much of that content was being tested, if that makes sense. I should say in this half, there does seem to be, just by fluke, a bit more concentration on calculations. So when I run through those, I'll try and lay them out as, purposefully and neatly as I can. But it's important that if you are reviewing those questions in your practice, you take the time to, I'll probably pause the video, and construct your answers prioritising the layout. And I'll say that till I'm blue in the face. The layout is the most important process here, particularly for calculations that are a bit more problem solving based. If you've got a solid layout for how to attain certain values, numbers of moles, working underneath certain chemicals, underneath an equation or whatever, then I would prioritise that if I were you, making it nice and neat. Right, I'm going to fire in then. So the first question, which is question 8, continuing directly on from the first week. Straight away, this is a unit 2 question, and it's a classic layout of experimental determination of structure. And what I mean by that is part A follows on right through to part D, and you're kind of aggregating the work that you're doing throughout to get to a final answer. You're building up pieces of an ongoing puzzle. Now with that in mind, if you make a mistake early on and you carry that mistake through, you can expect to be able to earn carry through marks, not at every single question, but certainly the majority of it. So never panic in the situation where you think you've kind of fluffed up the first part. You can still earn the majority, if not all of the marks in later parts of the question. Anyway, so it discusses the uses of phenylbutazone and how it can be synthesised in a multi-step process starting from compound A, and it wants us ultimately to figure out the full structure of compound A. So it starts us off with empirical formula, so a ratio of, in this case, carbons to hydrogens to oxygens. Remember, in empirical formula you can be asked 2 variants. In this one, which I would argue is the easier one because they've done some of the work for you, you're presented with percentage ratios for each of the elements contained. And so in this one, you don't have to figure out the extra steps in the other type, which would be starting from masses obtained from the combustion. And then you would have to figure out the percentage ratios from there. So in this example, we don't have to do that. So what we can do is treat these percentages as masses if we assume that the starting mass of the full compound is 100 grams. At that point, we can assume that we've got 50 grams of carbon, 5.6 of hydrogen, 44.4 of oxygen. So that's where I'm going to start. So I'm basically using those percentages effectively as masses. But I'm still going to write the percentage symbol at the side. But you know that they're interchangeable for the next part of the process. So we've got 50, 5.6. You'll notice that I'm including all and any significant figures that are mentioned in the question. It's just good for continuity when you can see when you're looking back at your question. By the end, how many significant figures should you be using? So the next thing we're going to do is convert this into something a bit more useful. We want ultimately to get a ratio of each one based on masses. So what we need is numbers of moles to get us to the point where the masses are not contributing to the ratio internally, if that makes sense. So what I mean by that is we can't work between different elements if it's just in percentage or raw mass. We need to relativize it to each other. So we need a mole ratio. So we'll do that by dividing each number by the relative atomic mass of the element. This is not the example where we divide by the GFM of the compound that it came from, because we already have the isolated numbers of each element. So we would have to divide by the GFM of the compound, say CO2, water, and find out the remainder that's oxygen if we start with that information. But as I said, this one is a little bit easier than that. So it's the RAM in the data book. These are just isolated elements at this point. So we divide by their individual RAMs. And when we work that out, we find that that is 4.1. And then those numbers. Place. I was actually so heavily distracted by 6, 7 there. That's really unfortunate. Well, it's just ruining my life at every opportunity at this point. Okay, so now what we have is the numbers of moles, and what I can now do is represent these as a sort of more simplified ratio by dividing by the smallest one, and then we're setting the ratio relative to that mass, or that number of moles I should say. So we'll take 4.167 divided by 2.78, which is the smallest value, so we're setting that relative to 1, making it the smallest thing. And then we are dividing 5.60 by that. And then itself by that. So we end up with 1.499. Now really, I don't have to be too careful with the rounding here, because ultimately what I'm going to end up with is whole numbers anyway. So at this point, I'm going to say that this is roughly equivalent. It's that little kind of funny squiggly line on top equals symbol there. Roughly 1.5 to 2 to 1. So the rounding at that point didn't really matter, because I'm roughly going to get the same number anyway. And therefore, because we can't have half of an atom in an empirical formula, therefore that's roughly equal to, if we double everything, 3 to 4 to 2, which means my empirical formula will be 3 of them, 4 of them, 2 of them. So C3H4O2. So just in terms of the marking there, it's worth 2 marks. So just to make sure that we're actually getting awarded partial marks if we do end up making a daft mistake later on, if you know to divide by these numbers here, pardon me, as in using the RAMs appropriately, you get awarded a mark. And then obviously the final answer is worth a mark as well. Part B, we're kind of building the case up as we go. Now this one doesn't include any mass spec data. It usually would, in order to get us to determine a molecular formula next. Okay, now there is mass spec later on, but in this case we go straight to the IR, and we're kind of skipping a step here, but it doesn't matter, because all we're asking to be done is to identify the functional group responsible for a given peak. So there's kind of 2 approaches to this question. The proper way to do it would be to look up the data book values that have ranges that match these corresponding characteristic peaks. And remember, these peaks are corresponding to behaviours of certain bonds, so they're very characteristic. And this one in particular is characteristic to a carbonyl stretch. Okay, so that technically is the functional group, but that one specifically actually corresponds directly to a carboxyl or a carbonyl group, and you're allowed to quote both. C double bond O stretch, that specifically is the functional group that you're looking to identify, but if you identify it as a carboxyl or a carboxylic acid stretch, then that's also fine. It does say in the guidance that a mark should not be awarded for carboxyl or carboxylic acid by itself. So let me just clarify what it means by that, because I've just written this. If you did identify it as a carboxyl or drew this carboxyl group, you would have to say that it was from this stretch within that group, because it's this particular bond that's causing the behaviour. It's not the full thing, right? So it's the carbonyl stretch within the carboxyl. So really, the proper answer would be C double bond O, or C double bond O stretch, or just the word itself, which is carbonyl. That's the best answer for that question. Mass spec data. We're not needing to extract too much for this first part. Write the molecular formula, nice and simple. We go to the furthest along peak. That's the molecular ion. And then everything else is a fragment from the main molecular ion. And by molecular ion, we just mean whatever the molecular formula is, but with a positive charge overall, like that. Reason being, it's lost an outer electron, from the molecule as a whole, so it's the same GFM, but with a positive charge. And obviously the charge doesn't affect the gram formula mass, so we can assume that number there is the GFM. And if we pair that with our empirical formula from before, we find that it matches exactly. For part 2, we do have to think about fragmentation a little bit, so suggest a possible ion fragment that may be responsible for the peak at MZ mass to charge ratio 27. So effectively remember that this number corresponds to the gram formula mass of whatever that fragment is. Now what we should pay attention to is how tall this peak is. That indicates that there's quite a lot of that fragment that was collected, right? So if we look at the percentage here, in almost 100% of the cases, individual molecules I suppose, there was a fragment collected at mass to charge ratio 27. That suggests that it's a stable ion fragment. So it's something that logically could exist on its own without falling apart for a relatively large amount of time. Now we're talking about seconds here, milliseconds if anything, but relative to the other fragments which maybe would be much less stable, this is something that's got to make sense. So essentially the way to do this is to play around with the masses of the elements, the atoms that you have involved, until you get something that makes sense, right? So C2H3 would make sense for two reasons. First of all, if we think about the structure of that fragment, okay, think about the carbons and their valencies, the hydrogens and their valencies, having something that's been fragmented like that probably makes sense, because that's something that could be relatively stable as opposed to something that's maybe got like one carbon, one hydrogen, one oxygen, something like that, because of the types of bonds that we have here. Also, it needs to be a fragment of the original molecule. So we're assuming here that there is a carbon chain of 3. So we're going to have to basically break things off of what we're kind of visualizing as an overall structure here, something that would be left. So we can't just rearrange atoms that wouldn't already be bonded, and that's really important. So my advice for this particular question would be, once you consider all the evidence, draw a full structure for it, go back and start taking things off of that structure and seeing if the fragment is possible, because you can't rearrange things, right? Things don't rearrange, they just fall apart from the original structure. And then the last thing to comment on, which is very important, you wouldn't get a mark for this, even though the GFM would be correct. Okay, it adds up to 27, but it's an ion fragment. Ions have a charge. Okay, it's always a positive ion that's generated in mass spec, even the molecular ion, because it's called an ion. So considering all the evidence then, well, what do we know? We know that this is a fragment. We know that it's got a functional group of C double bond O. We know that it's got to have exactly 3 carbons, 4 hydrogens and 2 oxygens. And so a possible structure for that is looking something like that there. So you're thinking, okay, well, how would you know to have this specific functional group with those 2 oxygens? If you start playing around with the molecule, you realise that you do need a double bond here somewhere. It makes sense to distribute things like this. So once you start doing a process of elimination, it's quite difficult to not arrive at the correct conclusion. Okay, for question 9, we flick back to Unit 1. We're looking at acids and bases, and we're starting with sort of definitional stuff here. So for the first one definition for acids and bases was proposed by Bronsted and Lowry. You've simply to give a definition for that. So there's kind of 3 ways towards this. The word acceptor has to be used. It's either a proton acceptor, a hydrogen ion acceptor, or an H plus acceptor. You cannot write this, okay? Or hydrogen acceptor, that's not accurate. Hydrogen, or the symbol H on its own, is not representative of a proton. That's a proton and an electron. So if you use the symbol, you must use a plus. And if you say hydrogen, you must use the word ion after it. I personally would play it safe and write the word itself. So it's a proton acceptor. Based on that, if you got that definition correct, this next stage should have been quite simple. You're identifying an acid with its conjugate base. So bearing in mind this behaviour, if it's something that, if a base is something that accepts a proton, an acid is something that loses a proton. And it's a case of choosing a pair then. So in this case, the hydrogen peroxide is acting as an acid because it donates a proton to something else, forming the hydronium, which is the conjugate base. That's just not true. There's a way in one world there. It forms the HO2 minus, by donating one of the hydrogen ions. And then alternatively, we could have the opposite direction. Technically, we could reverse this reaction, right? And we could go from the hydronium back to the water. And in that case, we would also be going from there to there, donating a proton. Best answer is this one because it follows the forward reaction. But in the marking scheme, this is also accepted. You've got to have both in the right places, and if there's charges, you must show them. Okay. State symbols you don't need to have, but usual rules for state symbols and units, if they're there, if given, they must be correct. That age-old SQA statement. You're then given some information about the behaviour of Gilbert-Lewis structures, so a Lewis acid and a Lewis base. And this kind of shifts the definition to discussing non-bonding electrons. So a Lewis acid can accept electrons and a Lewis base can donate electrons. So it's kind of the opposite of the Bronsted-Lowry definition. That's an easy way to think about it. So explain, based on this equation here, why this is a Lewis acid-base reaction. You've got to use specific compounds that feature in the question in order to explain this. And that's, you bringing in the specific equation there. So in an explanation, we have to say that, firstly, BOH with 3 of those accepts electrons and water donates electrons. Now, the language of a pair of unpaired or a pair of non-bonding electrons isn't necessary as long as you get the acceptance and the donation round the correct way. And that's the mark for that. For part C, you're given some information about these K values, Ka values, dissociation constants of some acids. And for this particular question, you don't actually need to use these numbers directly in terms of a calculation. This is something that can be looked at in Unit 1 with acids and bases, but this question doesn't require you to do that. It will be used as a trend though. State what's meant by a weak acid. For this question, you had to use the language of partially dissociated ions in aqueous solution, or acids that don't readily dissociate or dissociate poorly, anything to do with the idea that it doesn't readily fully dissociate into its ions was accepted. Then for part 2, describe the relationship between the number of chlorine atoms in an acid and the strength of that acid. For this particular case, it seems to be that as the number of chlorine atoms increases, the strength of the acid also increases because this number is increasing. And we can realise that because Ka is the dissociation constant. So the larger this number, the higher the degree of dissociation. So the fact that that increases as this increases gives that trend away. And that's the end of that question. For question 10, we are back to Unit 2. This one hopefully was relatively straightforward. We're doing some counting first of all, so we're given some information about glucose and fructose syrup because they're types of sugars. We're told about some obesity information, but that's not really relevant to getting the marks. But we are told that there's ring structures for both of these sugars, and it's given in a mainly skeletal format. So we need to write the molecular formula for fructose, so that's obviously this one. In your approach to this, I'll not do it here, but you really should take the time to write this out as a full structural formula, and that's going to allow you to see little sneaky details. So for example, if you clock that this little corner here is a carbon, in your rush to do the question, you might not also remember that there's a little pair of hydrogens attached to that as well, because there's only 2 points of valency used for that carbon in the diagram, whereas it must always add up to 4. So something to watch out for. So if we just count them quickly, we'd expect to find 1, 2, 3, 4, 5, 6 carbons. We're then looking at 1, 2, 3, and on here, 4, 5, 6, 7, 8, 9, 10, 11. Have I missed one? Have I done something daft there? Oh, and a 12th one on there. See, that was confusing even me. So the reason why I missed that one there is because in quickly looking at the diagram, much like this one, this side and this side are mirrored. whereas this one's got an extra substituted group here, so it might be easy enough to miss off that little extra hydrogen there. So 12 hydrogens in total, and then 6 oxygens. 1, 2, 3, 4, 5, 6. So overall, C6, H12, O6. If you don't believe me, draw it out. Part 2 suggests, with reference to the structures, how proton NMR spectroscopy could be used to distinguish between glucose and fructose. This question is notoriously poorly done for not using specific enough language that actually relates it to how NMR works, or how proton NMR works. So you need to relate it to something to do with how that would be read as a spectrum. So any one of the following concepts would earn a mark. Different number of peaks, or different number of protons, or different number of hydrogen environments. Okay. Now, to be clear there, when I said different number of protons, all of those answers are expected to be followed by the word environment. So hydrogen environment, proton environment. Peaks as a standalone is fine, but you can't just say number of protons. Okay. Different shift patterns would also be acceptable. Different splitting patterns or different multiplets I would accept. Even the language number of sub-peaks, in inverted commas, is included in the marking scheme. I would avoid that. I would avoid non-standard language if you can. If you forget what a concept is called, so you forgot, for example, that it was called multiplets or splitting patterns, maybe just draw a diagram to make sure that the examiner knows that you know what you're talking about. So if you said something like sub-peaks, which is non-SQA language, draw a diagram, right, just in case you forget what a term is. And then the last one, a bit more niche, different peak area / heights / integrals is also accepted, because obviously different multiplets would result in different peak areas. Additional guidance is quite thorough for this one. Any mention of a different number of carbon or hydrogen or OH group or atoms is a cancelling error, right, because it's not true. Any mention of hydrogen environments / shifts that do not exist in either sugar is a cancelling error, e.g. CH3, aromatic, benzene. Any discussion of something that's not there, even if you have written the right information, is going to cancel the correct information. And then different spectra on its own, just as a statement, is not acceptable. Part B, a more accurate representation of the structure of glucose and its geometric isomer galactose, great name, is shown below. Right, this is something called a chair conformer, and this is used to show some 3D geometry of the molecule, because really when we look at the carbon bond angles, we find that they mirror little tetrahedrons. So drawing it in any other way except for this is actually quite inaccurate. With reference to the structures shown, circle that for now because I'm going to come back to it. Explain why sugars such as these have geometric isomers. So definitionally, from your notes, you should recall that geometric isomers generally exist with things that have double bonds, or in other words, a lack of free rotation around the double bond. Now, if you'd just said a lack of free rotation for the answer for this, that would earn you a mark. If you then mention double bonds, it's a cancelling error because there's no double bonds present here. The deepening line density here, right, the kind of thick lines that were shown at the front here are just to show the fact that these bonds are, if you like, coming out of the plane of the paper. So it's just to show the geometry. They're single bonds, right? There's no double bonds here. So the thing that locks the orientation in, the thing that makes it lack free rotation, is the cyclic structure, or the ring structure. That's what restricts the rotation. So any mention of double bonds would be a cancelling error, but you do need to mention a lack of free rotation. It goes without saying anything in the way of discussion of optical isomerism, so talking about non-superimposable mirror images, that's a different concept entirely. So if you've mentioned that, you've got yourself quite confused, and that's obviously not a correct answer. So a lack of free rotation around the ring structures would be my perfect answer for that one. Question C is quite odd, because it's drawn strangely for what it's actually asking you to do. So it says the ring structure of glucose exists in equilibrium with its open chain structure. So essentially this can change to this. It's called D-glucose. State the number of chiral centres. Now what's important about this one is for each individual chiral centre, of which there are 4 in this particular molecule, you need to realise that there are 4 distinct groups. So they're all singly bonded. So they've got 4 distinct groups, which is one of the criterion. And in each case, they're all different, right? But you need to look at the entire extension of what what is attached to each individual carbon. So I think some people maybe ended up getting confused here. Say we choose this one here, and they were looking and they were saying, well, directly bonded to this is a hydrogen and an OH, so they're different so far. However, when they looked at this carbon and this carbon, they saw, okay, it's bonded itself to a hydrogen and an OH, so that doesn't count. You have to take into account the full thing that's bonded relative to the carbon that you're examining. So in that case, they would be different. So that means there's actually 4 and not 1 or 2. And drawing an open chain structural formula for this, it's quite tricky to do because they're giving you a poor diagram to work with. What you really have to do is choose one of those chiral centres and sort of flip what you're given. Some people had some interesting interpretations of this, just simply flipping it round. That's not a mirror image, it's just the same molecule, right? Because in the examples that you have in literature, your notes, whatever, anytime they simply flip the molecule around, they've done so after showing the geometry of the molecule. This one doesn't. So it would be, for example, if we had a carbon that was drawn with full molecular geometry, and let's just say it's got groups A, B, D, and E. If we then draw the mirror image on the other side of that, so, you know, literally just drawn the mirror image of it, right, like so, that would be an appropriate answer because we're showing that this, in fact, is different from this. If you then take this and you rotate the groups so as that E is back over here, like it is over here, you'll find that D and B have changed places. Okay, so if you imagine this, and you imagine this axis of rotation, and you spin it round 120 degrees so as that the E goes back to its original position, as you can see, B would go there, and D would go there, based on that rotation, which is not the same as you see here. So that's an appropriate answer for this. You can't do that for this. You can't just simply flip it because there's no geometry shown. So what you have to do is sort of internally flip one of the chiral centres relative to the other ones. So essentially what I'm saying is, if you flipped any of these carbons on its head, so for example, for this first one, let's just call that centre 1. If you flip that so as that the OH was at the bottom and the H was at the top, but kept everything else the same, you would earn a mark for that question. So I think the SQ have been unfair there in that they are giving a non-optically diagrammatic image for something that requires you to use optical isomerism. I think they should have given you full geometry there to play with, but we know what they're like. So that's how you tackled that question. It goes without saying that you could have chosen any of the chiral centres for that. The question continues, a bit more about isomerism and functional groups. This is the drug known as Relenza. It's a medicine used to treat flu virus, and tells us importantly in the description, it acts by attaching to an enzyme active site. So straight away I'm thinking we're going to have to consider types of intermolecular forces here. But remember, it's important to take into account the geometry of the molecule as well, the size of the molecule. It's not just forces we have to consider, it's orientation, size and shape. So that's a bit of foreshadowing for part 2 of this question, which a lot of people got wrong. Part 1 suggests how the functional group circled in the Relenza molecule would bind with part of the enzyme active site. They're circled here, it's clearly N to H bonds, so clearly this is acting as a sort of lock and key situation, and what the interaction would be is hydrogen bonds. So hydrogen bonding, or dative covalent bonding actually would also have been accepted. The reason for that is because the nitrogens themselves do in fact have lone pairs. So they could act as a sort of ligand-like structure with the active enzyme site, or the enzyme active site, I should say. But hydrogen bonding was probably your go-to answer there. I should say any other intermolecular force should not be treated as a cancelling error. Okay. Ionic interactions, though, are incorrect because this is a covalent molecule. So the correct answer is hydrogen bonding, but it's not incorrect to say that it could be PD-PDI, for example. So something to bear in mind. It's not a cancelling error, that is. Okay, but we have to target the exact interaction that we have, which is hydrogen bonding. For part 2, bearing that in mind, this is a molecule that behaves in a very similar way. We have to circle the functional groups on this molecule, which are most likely to bind with the same enzyme active site. So if we imagine this was the area that was doing the binding before, we know that it must be roughly that size, right? So in the marking scheme, it identifies this group, and this group here. Now, a couple of follow-up things to consider. First thing, why is it the OH groups? Because they behave similarly to the NH groups, right? It's still hydrogen bonding, so they're appropriate. Locationally, it makes sense, right? This is the side of the molecule that was doing the interactions before, so it makes sense that it would do the same thing here. Lastly, think about the area that these cover. In the marking scheme, it says a minimum of 2 of the 3 circled OH groups must be present. So circling all 3 is fine. Circling 2 of the 3 is fine. 1 on its own would not be appropriate because it's both of these groups in the first instance. So it must be at least 2 down here just to cover that size. Because what we would be saying is just a single point interaction like that doesn't compare with our kind of double interaction that we've got up here. So clearly the enzyme active site must be a bit larger, a bit wider than just 1 on its own. But 3 is also fine. You didn't have to get the 2 bang on. But a common mistake for this one would just be circling anything that's got hydrogen bonding interactions or even PD-PDIs, and that's not appropriate because these areas are not identified even though they exist on the original molecule, so they're not appropriate. And that's that one done. Question 11 was hopefully a relatively straightforward counting exercise. In this question we're told a little bit about the definition of paramagnetism and how it's caused by the presence of unpaired electrons. In both these 2 complexes here, we're told that the Fe2 plus ion has 6 d electrons, but only one of them is paramagnetic. Okay, we're then told to focus on the other one. Now we've been given the information already that it's an Fe2 plus ion. I'm going to write that there because that's important. What do we know about that? We know that it contains 6 d electrons. Okay, so 6 d electrons. So what we need to do is think about how we're going to populate those electrons in our diagram. We've got a couple of options. We could fill everything singly, 1, 2, 3, 4, 5, and then place a 6th in here. Or we could pair things up, so we could have 1, 2, 3, 4, 5, 6. Clearly these are different. We need to pay attention to the definition. Paramagnetism is caused by the presence of unpaired electrons, and we are told that only this version of the ion is paramagnetic. So this one is not paramagnetic. Therefore, it must have no unpaired electrons. Therefore, the most appropriate answer is pairing all of the electrons up. So we should note as well that this follows our rules for filling of orbital box notation because we don't have a small enough energy gap through which to promote electrons before pairing them. And that's what would cause that kind of difference. You'll notice in the 2 complexes that are given that the ligands are the thing that has changed. So clearly one is a stronger field splitting ligand than the other. So in the case of the cyano group, cyan, or the cyano ligand is a stronger field ligand, so we'll split the energy field greater, so it forces the electrons to pair up rather than splitting them across the 2 non-degenerate sets of orbitals. Pardon me. So that's that one. Part 2, the relative ability of a ligand to split the d orbitals when forming a complex ion is given by the spectrochemical series, and then we're kind of detailed below what I've just said there. So clearly this is stronger than this, which are the 2 that we're considering. The FeH2O62 plus ion has unpaired electrons and is therefore paramagnetic. Explain how unpaired electrons can arise in this complex ion. So the information that it's looking for here, because it's 2 marks, is 2 separate ideas. 1 mark is awarded for recognising that there's a small energy gap because of the weak field splitting ligand, but it's just the small energy gap, that's the key word you need to use there, but that's the reason why. And then secondly, another mark's awarded for recognising that the electrons therefore are promoted, so they jump from here to here, because remember this is the preferred state to pair, the preferred state is to be singly occupying rather than pairing. So the jump is made before they pair off, ideally, if possible. But in the instance like we have here, where the field is simply too wide, that promotion can't happen, so they're forced to pair rather than making the jump, which is why it does this, which doesn't obey that rule. Part 3, explain why all of the complex ions formed by the Fe3 plus ion are paramagnetic, and there's no variation there. You could have worded this in several ways. However, a mark should not be awarded for just saying simply it has an unpaired electron. That's not quite enough. You've got to explain why that is the case. So something along the lines of it's got 5 or an odd number of d electrons would be fine. Saying that it is 3d5 on its own would be fine, that would get you the mark. Or saying, and this would be my preference, saying that it's got a half-filled d orbital or d subshell in total would be probably the most appropriate response. So we've got an odd number, one of the electron orbitals must be unpaired, must have an unpaired electron in it. And that is what gives rise to the paramagnetism, so that explains that. Part B looks complicated, but it's actually fairly simple. So when asked, firstly, if I just jump to the actual question itself, state the coordination number of Fe2 plus in hemoglobin. Well, if we find hemoglobin, we just have to simply look at how many points of contact there are between what is a monodentate ligand, because it's all joined, and the central metal ion itself. So there's 1, 2, 3, 4. So the coordination number, funnily enough, is 4. Part 2 then discusses spider's blood and how it contains oxyhemocyanin as opposed to hemoglobin. So it's based on a different metal. It's based on copper, which, just out of interest, is what causes the colour of the blood to be different. So the fact that it's a different complex based on a different metal ion is what gives rise to arachnids, well, particularly spiders anyway, having blue blood. It then asks us to suggest an analytical technique that could be used to determine the presence of copper, and really what I'd be looking for there is either flame test, because we could burn the sample, or atomic absorption or atomic emission spectra. Those would be the most appropriate, because we want to see just the behaviour of the metal ion there, and that would help us isolate that based on wavelength properties. So flame test or AAS or AES would be appropriate. Question 12 is quite a dense synthetic chemistry question. It's starting by saying a student devised the following reaction scheme starting with 1-methyl cyclohexene, which is here, and then it goes in a variety of directions and branches, but we're just dealing with isolated things at a time, making sense of times where the reaction splits into 2 possibilities, like in step 1. So it tells us in reaction 1, where it reacts with HBr, it produces 2 compounds. Draw a structural formula for compound X, which is clearly the alternative to whatever this one is. So if this was already produced, you'd be amazed at the number of people who then just put this, but then switch these 2 things round. My dude, that's the same thing. So that's not accepted, right? We have to think about how this double bond behaves if it was to bond alternatively. So we should show the breaking of the unsaturation, so it should be a single bond. The CH3 doesn't go anywhere, it's already there. It's just that the Br bonds to the other carbon instead. It does then tell us that reaction 1 obeys Markovnikov's rule. Explain why compound X is the minor product. Now, crucially, it says with reference to the carbocation intermediate. So if that's not in your answer, you're not going to be awarded the mark. I really should have put a warning in about a potentially very loud noise there. I hope that doesn't come across too loud on the recording, but it was loud for me. Yeah, so we have to mention this carbocation intermediate, and if we don't, we're not going to get the mark. So, in simple terms, Markovnikov's rule states that in a situation where there's a carbon-to-carbon double bond and we're going to perform electrophilic addition, let's say on this carbon we have a proton, or a hydrogen I should say, and that bonds to the rest of a chain, and let's say these 2 carbons bond to multiple parts of multiple chains or multiple branches that are carbon-based. Markovnikov's rule says if we have a hydrogen bonded to something else and we're wondering which way around these bond, the hydrogen always goes to the carbon that already contains the highest concentration of hydrogens on it. That's the simple definition. This is asking why that is true, not for you to state that. That's not the answer. So the answers might include the fact that the less stable or unstable carbocation is how the minor product would be formed. So the most stable carbocation, of course, would be if this was made to be positive, because it's surrounded by not one, but two inductive effect groups, right, where the multiple electrons can sort of support the existence of a positive charge. Whereas if we form the carbocation over here, that wouldn't be the case. So remembering that whichever one the carbocation is formed at is where the non-hydrogen goes, right? So if this was our carbocation, we would expect to see the Br to go in there, and we would expect to see the hydrogen to go in there, right? That only happens because this is the most stable one. So in our explanation, we should say for the minor product, the carbocation on this side is less stable, or you could flip it and say the more stable carbocation is tertiary, or is more substituted, or has alkyl groups, or whatever it is you want to say. The guidance is quite thick on this one. It says an answer that refers to the number of hydrogens only with no reference to the stability of the intermediate is not acceptable, because that language is used in the question, of course. Or an answer that refers to a more stable carbocation, forming compound X should be treated as a cancelling error because you've got it the wrong way around. Okay, but you had to mention that. You don't need a diagram, but you did have to mention that it was less stable in the minor product. This question continues. Suggest a reagent that could be used in reaction 2. Reaction 2 is this one here, where we're converting the cyano group to the corresponding carboxylic acid. That is an example of acid hydrolysis. It comes up as a kind of secondary reaction to a classic nucleophilic substitution reaction with the hydrogen cyanide or the cyano ligand all the time. So you should kind of just have that memorized. The key mistake here is that we need to have multiple things going on. So hydrochloric acid probably would be the most sensible answer. However, it has to be aqueous. So you have to indicate that the H plus is in water, is in solution, is AQ / water, or H plus and water, or really any named acid as long as it's dilute or aqueous. You had to mention the fact that it's in solution. But just getting the fact that it was acidic is enough. You don't even have to state the type of acid, as long as you provide the H plus ions to acid hydrolyze the situation. Because remember, hydrolysis happens by adding water, so it has to be there. And it's acid hydrolysis, so it has to be done in an acid. Reaction 3 is likely to undergo an SN1 mechanism. We have to then use curly arrow notation to draw the mechanism for this reaction. It's only worth 2 marks. So what's important here is that we include the right level of detail at the right points. So firstly, SN1 means that there's 2 steps, and you're essentially being awarded a mark for each step. So the first step would be redrawing this molecule that I've circled and indicating that we are going to lose the leaving group first. We need to create an electrophile into which a nucleophile is going to attack. Now, just a quick bit of background to kind of rationalise this. Why is this SN1? Well, there's a big steric effect. We have to attack this carbon here to substitute on an OH group. We're going to have to remove this bromine first before the nucleophile has space to come in because of steric hindrance. There's also an inductive effect on this carbon. Right? It would form a tertiary carbocation, which would be very stable because of the inductive effect. So that's 2 reasons why it would be SN1. But anyway, if we think about the first mark, I'm actually going to redraw that because that's getting a little bit messy there. So I'm just going to draw this as you should have drawn it in your answer, and then I'll zoom in to make things really clear, hopefully. So we've got our initial product, or initial reactant in this case, and we want to show the leaving of the leaving group. So when we're doing this, we have to show where the electrons are coming from. So the line starts bang in the middle of the bond and where they're going to. It's a full-headed arrow because it's a pair of electrons. So going from the bond to the atom or to the nucleus of wherever they're aiming for is appropriate. Major arrow shows that we know we're moving on to a different step. And what we're looking for here mainly is that you've formed the carbocation properly. So what we should see is, I'm going to draw this upright so that it's out of the way. What we should see now that this is missing something, this should be a positive centre there, ready to be attacked. So it's a carbocation. You could draw it as an individual letter C with a positive charge at the top right. That's fine too. I just think that's easier to see. And then the nucleophile itself is just the OH minus. So some people indicated that this was also maybe in solution with Na+, but drew the full compound, so drew NaOH. The only time you would get a mark from here is what we need to show is the nucleophile coming in and attacking the positive centre. And I don't even need to draw the product because the product's given in the question. This is where you get the second mark. You only get the second mark if you drew it like this, if you draw the arrow coming from the oxygen. If you drew it coming from the space in between, or the Na, or the H, then you wouldn't get the mark. So I would discourage you from drawing a formulae like that, because it's also not indicative of the reality of the situation. In reality, in solution, there's Na pluses, there's OH minuses, there's water molecules, right? There's not directly bonded Na to OHs, so that actually doesn't make much sense. I think just by the skin of your teeth you would get the mark if you drew the arrow coming from the oxygen, but I would encourage you to isolate whatever the nucleophile actually is. Remember, a part of a substance is nucleophilic. It's an individual species, so an ion, a particular atom, whatever it is, rarely is it the whole substance itself, unless that substance has like a lone pair or something like that. Part D, you just simply have to name compound Y. I say simply, compound Y is relatively complicated. It's got a cyclic group, it's got an ether, and it's got a methyl group. So we just have to be careful, we have to base it on what we're already given. So the fact that this is 1-methyl cyclohexene, we can sort of use this naming to help us here, because all we've done is change it from hexene to hexane, because the double bond's been broken, and we've added on an ether branch. So we just have to remember about how we name that. So the absolutely correct answer would be 1-methoxy, because the alkoxy group used has got 1 carbon in its chain, so it's a methoxy group. We're introducing another number, so I'll use another dash. Also on carbon 1 is the methyl branch that's always been there, and then cyclohexane from there. They were accepting quite a few variants here. 1-methyl, 1-methoxy, so switching these round was fine. 1-methyl methoxy, so just convolving both onto the 1 was fine, although I don't agree with that. Methyl 1-methoxy, because it's implied where the methyl group is if you don't use a number, was also fine. 1-methoxymethyl or methoxy 1-methyl were also fine. I would encourage you, just anytime you're discussing a different branch or a different group, use a separate number. Methoxymethyl cyclohexane is not acceptable with no number because it doesn't indicate that they're on different parts of the ring. 1,1 methyl methoxy were not accepted, regardless of the way around that you worded the two groups. Putting 1,1 is usually the nomenclature that's used if whatever the group is the same type of group. So you would use di and then the name of the group in that instance. If it's a different word, you have to use a different spacing of that number. You have to repeat it basically because it's for a different thing. And then, this should go without saying, any name ending in "-ine" obviously wouldn't get you the mark. But that would have been a really daft mistake if you made it. Moving on to question 13, which is about Roman pottery, of course. Metals present in Roman pottery can be identified using atomic emission spectroscopy. So then we're given some wavelength of spectral lines information, and then something called the relative intensity of those lines. That's usually to do with a concentration of a material in a sample. Obviously how intense the line is comes from how concentrated the thing is. Name the metal that produces the orange-yellow spectral line at 589. I think everybody got this right. Based on its wavelength, it should have been sodium. Now in the marking scheme, they are accepting Na, but anytime it says name, please just write the name in full, just to make sure, because sometimes they're a bit more picky than that. A fourth line is observed in the spectrum obtained from the Roman pot sample, which caused by a transition with an energy value of 282 kilojoules per mole. Calculate the wavelength in nanometers of this spectral line. So this should be simple if you lay out your calculation nice and neatly, so that's what I'm going to attempt to do here. So I'm first of all going to identify the relationship that we're using. Energy is equal to L times H times C divided by factor of 1,000 of the wavelength. So to be clear, that's Avogadro's constant times Planck's constant times the speed of light in meters per second divided by lambda, but we're putting in the 1,000 because if we don't, this answer would be given in joules, and we're working in kilojoules because that's generally the range of the values that we're given. If we worked in joules, we would be working in the hundreds of thousands of joules, so it's just not the appropriate unit to use here. So if we take our equation and we set it equivalent to something that's useful, because what we actually want to find is that one, we basically just switch the position of the energy in the lambda. It's a nice easy way to do it. So lambda equals L times H times C divided by 1,000 energies. So if I go ahead and do the substitutions, which I'm going to do now off camera to make this a little bit quicker. Okay, there we go. So Avogadro's, Planck's, speed of light, using 2 decimal places, 1,000 and 282 on the bottom. When I process those numbers in my calculator, I get 4 point... Oh, I'm just going to do this live actually, just to show you the way that I input it. It's probably more useful actually. What I do is the top line and the bottom line separately, but I keep the information in the calculator. So 6.02, and then just this button here to get times 10 to the power, times 10 to the power of 23. Feel free to skip this section if you're confident with this calculation. Apologies for the grandpa speed typing there. So we've got this value on top. I'm going to divide that by, in brackets, 1,000 times our energy. Just gathers all those like terms there. So that gives us 4.246, etc. This is probably fine for the amount of rounding that we're going to do at the end anyway. And that is times 10 to the minus 7. So this is the bit that most people kind of get wrong. So you've got a mark so far if you've managed to correctly substitute and process those numbers. This number that we've obtained is in meters because the speed of light is measured in meters per second. And the seconds and per seconds have cancelled out given the values that we're using. So we're left with just meters. Remember, to go from meters to nanometers, that's times 10 by a factor of 9. So times 10 to the 9. And so going from minus 7 and then timesing it up by 9, of course, for surds and indices, if it's an index and we're multiplying 2 terms, we add the powers. So minus 7 plus 9 gets us to the power of 2. So that brings us to 4.246 times 10 to the power of 2. And if I just write that out as a whole number, it's 424.6, which can roughly round to 425. And I'm rounding it to that because that's the lowest level of significance that I have in the question. So 425 or 425 nanometers, but we're explicitly asked to give the answer in nanometers, so it must be in this. So I think the main weakness for people here was going from there to there. Remember, whatever number this is, it's in meters, and to go from meters to nanometers, you basically add a 9 onto the power that you already have, and that's how we get that answer. For part 3, the Roman pot sample was found to have a titanium content of 435 milligrams per kilogram. A different pot sample produced a spectral line at 498 with a relative intensity of 75. Calculate the titanium content for this sample. So the calculation we're having to do here is we're saying relative intensity of 375, right? So we're talking about the pot sample with a spectral line at 498. So I'm correlating that bit of data with that bit of data and matching it up to this relative intensity, because that's the one for titanium. Right. And I'm using that to say, okay, from this value here, I can set that to be the titanium content of 435 milligrams per kilogram, because that is essentially what I'm told here, right? The pot sample is found to have this content, okay, and we know that we're operating at this wavelength, so we can correlate that to our previously identified relative intensity. So what we want to figure out is, okay, if the relative intensity changed at that same wavelength, but it changed to 75, what would be the titanium content? So obviously if the intensity is lower than 375, we would expect the titanium content to be lower as well. It's often good to kind of project ahead of time what you anticipate the value to be, so that you can kind of roughly check your answer. So a bit of cross multiplication. This value here is going to be this times this divided by this. That's the shortcut way that I do it anyway. If you're not happy with that, do this times this is equal to this times this, and then manipulate it to get x on its own. 75 times 435 divided by 375 gives us a value of, I think it works out to be 87. I'll just do that live so that you can check my work. So again, same method that I use all the time. Top line, so that I can press the equal sign and then just press divide straight after that to substitute in the answer automatically, rather than having to set up the fraction button and move around with the arrows and stuff. It's 6 1/2 a dozen, but that's my preference. 87, bang on, is the answer. So 87, technically it's in milligrams per kilogram as well. And that's all for 1 mark. It's a trickier one on the problem solving end for just a single mark in my opinion, but there we go. B is a little bit easier. It gives us some information about the electronic configuration of aluminium, and then asks us simply to state the Aufbau principle. So what we're looking for to say here is orbitals or shells or subshells or energy levels even are filled in order of increasing energy. I would prefer you said orbitals, to be honest, because that then accounts for situations where they're non-degenerate, but shells or subshells is fine as well. For this set of quantum numbers here for 3p, there's a little bit of slack allowed, so there's actually quite a few acceptable answers. So there's 6 acceptable answers actually, but they all start with the same 2 numbers, the same principal quantum number being actually identical to a number you're given in the question. So first of all, when we're dealing with 3p, this indicates some numbers straight away. The principal quantum number matches that shell number, and then the subshell here, right, the block essentially correlates to a value that will be somewhere from 0 up to 1 before the n value. So n minus 1. So what I mean by that is if it's ever an S, that's equal to 0. If it's an L, that's equal to 1. If it's an L, what am I talking about? If it's a P, sorry, L is equal to 1. If it's D, L is equal to 2. If it's F, L is equal to 3. Obviously F is off limits for this because n is 3, and at most L can be n minus 1. Physically, why is that true? Well, aluminium is limited by the fact that it only goes up to, for its electrons, it only goes up to the p block. There are no d electrons or f electrons, so it would never have a quantum number that had a value of L that wasn't 0 or 1 for that reason. That's the physical reason. But then the other reason is we have this number to follow as well. So in this case, the answer is 1. For the remaining quantum numbers, what we have to do is think about possible values for m relative to L. So what we do is we take minus L all the way up to 0, all the way up to positive L. So in this instance, if L is 1, m can either be minus 1, 0, or 1. And for each of these values, there's 2 spin states possible, a half or minus a half. Obviously, if we iterate that another twice, we can see that there's technically 6 possible answers here. So you could have had minus 1, and then plus a half or minus a half for that value. You could also have had 0, you could also have had plus 1, or just 1. So this, with one of these, that generates your 6 possible combinations, but you have to choose one. You've got to state one possible set. So follow the instructions carefully there. Moving on to question 14. This is about a titration practical. Hopefully not too bad. Hopefully not too confusing. Well, first of all, I mean, we're given a lot of information. I'll not read through that just now. You can pause the video and make sure that you've absorbed all of that information. I feel like half the battle with these styles of questions is the processing, right? Just taking the time to actually understand, start to finish, what is actually happening in this question. So if I just jump to where we need to calculate the answer for the first part, we need to calculate the number of moles of hydrogen peroxide in 20 centimetres cubed of the diluted solution of stain remover. So there's a few things going on there. We originally have a sample of stain remover, and clearly it was diluted because it was made up to the mark from a sample of 5 centimetres cubed right up to 100. So that's quite a significant dilution factor of 20 there. So it's something we're going to have to come back to. The volume that we're working from is that of the permanganate solution, which is what we've got the tighter volumetric data for three titrations actually. So we've got this titration here, here, and here. We're only interested in these two. This one does not count because it's not concordant with the other two. So we don't use the first titration. So our volume in use is the average of 18.5 and 18.6. So we'll take those numbers, add them, divide it by 2. Really, you could just do that in your head anyway. So 18.55 centimetres cubed, which is useless to us because we want it in litres. So 0.01855 litres. We then want the number of moles. So N is equal to C times V. The concentration we were using the permanganate is 0.03 or 0.030 moles per litre times that volume we've just averaged, and that gives us an answer of 5.565 times 10 to the minus 4 moles, and that is of the permanganate ion. Now if we look at the balanced equation above, it's 2 moles of that for every 5 moles of hydrogen peroxide. So if I bear that in mind, I have to take this number and use a 2 to 5 ratio. So the way that I do this in my head quickly is, if I have a number and I want rid of it, I divide by it. If I have a number and I want to bring it in, I multiply by it. So I'm going to take this number, I'm going to divide it by 2, I'm going to multiply it by 5, and in doing so, I will find that I get 1.39 times 10 to the minus 3. And it's moles, so that's just a number, and that's the final answer. So you would get a mark for correctly working out the number of moles of permanganate ions, and then a second mark for processing that into a correct number of moles using the mole ratio. Second question here. In fact, just before we move on, I should mention partial marking for that previous question. So correct use of number of moles to calculate moles of hydrogen peroxide, but from a wrong number of moles worked out here. So basically using a mole ratio correctly can still get you a mark, even if you fluffed up that first part of the question. And then just briefly, significant figure use. Remember, it's 1 below and 2 above. So technically, for this question, 1.39 is actually 1 above, because we are given, let me see where we're working from here. We're given 2 significant figures from our concentration. So really, the best answer should be 1.4 times 10 to the minus 3. So 1.39 is technically 1 above. That would make 1.391 2 above. So that means, if you're following my logic here, if this is the acceptable answer and we are allowed 1 below, you could technically give this as 1 times 10 to the minus 3 in your final answer, because it's 1 below 2 significant figures, which is 1 significant figure. As long as you evidence this, that then becomes an acceptable answer. I am making a plea to you now, please don't do that, right? And I mean, really instinctively you should be looking at that going, that seems silly, because it is. We wouldn't round like that, because we have significance above that. But technically the SQA accept it, one of the strange things that they accept. Moving on, calculate the concentration of hydrogen peroxide in the undiluted stain remover, and we're given our units that we have to use. There's a few steps to this one. So far, what do we know? We know that in the 20 centimetres cubed sample, I like to evidence everything that I'm doing, if I can, in these sort of larger, longer form calculations, right? What do we know? We know that we've got 1.39 times 10 to the minus 3 moles. Yes, I'm sticking with the heavier rounded number. Why not? Well, there's reasons why, but I feel like it. In 100 centimetres cubed then, because obviously in our practical, we've just taken a sample from a stock standard flask. So we're not dealing with all of the stain remover that we actually put into the flask and diluted. So we need to account for that by basically timesing our value by 5. So that's going to bring us out at 6.956 times 10 to the minus 3 moles. And then if we're dealing with the undiluted stain remover, what we need to bear in mind is we've got our number of moles in the diluted flask. The number of moles of the stain remover does not change if we've diluted it or not. It's the concentration that changes. So just to kind of run us through that logic, imagine you've got a glass with a tiny amount of undiluted orange juice in it. There's X number of moles in that glass currently. If I then take that glass and fill it up right to the top with water, it still contains the same number of moles of orange juice. It's still the same number of particles. It's just that I've added some water to it as well. So the concentration is definitely way, way lower per volume, because that's what concentration is. It's the amount of stuff in a volume, but the amount of stuff itself hasn't changed as a value. So in 100 centimetres cubed, there's that number of moles. In the undiluted 5 centimetres cubed, there's also that number of moles. So all we need to do is run a quick NCV. So concentration is number of moles divided by volume. The number of moles is 6.956 times 10 to the minus 3. And we're dividing it by a volume of 0.005 litres. That's 5 centimetres cubed. When we run that through, we find we get 1.39 moles per litre. And that's our second mark. First mark for knowing to do the multiplication to extract back to the 100 centimetres cubed. Second mark for correctly identifying the final answer there. Lastly, for this part, it wants to do a little bit of chemical analysis on the sample. So it's discussing how the concentration of peroxide determined was less than the stated on the label for the stain remover. They discuss a possible source of error being an inaccurate concentration of the permanganate solution. Describe how the student would confirm the concentration of the permanganate solution. For this one, you had to be quite specific. You had to say a titration with the standard solution or a solution of known concentration. You couldn't just say titrate it or use a standard solution. You had to say what you would actually do, because you're describing how the student would confirm. So you're having to actually state what the student would do. So a titration with a standard solution. Carry out colorimetry with a standard solution or a solution of known concentration would also be acceptable, but please remember you have to state both. So carry out colorimetry with a standard solution. So you can't just name the process or name the standard solution. You have to give the process and what you're using. It says in the guidance here, if standard or known solution is named, then it must be appropriate for a redox reaction, such as oxalic acid, hydrogen peroxide, etc. Standardising the permanganate solution without mention of titration is not acceptable. So a simple standardisation isn't acceptable. You have to mention the technique because it says describe. That's the giveaway. So it says describe, you're usually thinking about practical techniques or certainly a practical element to your answer to make sure it's a description of how they would do it, not just theoretically, but in a lab context. Part B of this question is our second using your knowledge question. Again, we're going to run that separately as a task. I'm going to go over that differently and separately, so I'm not going to cover the content here. Main reason for that, I should say, is that there's a wide range of answers acceptable and it warrants going over it in quite a bit of detail. Which brings us to our 15th and final question in the paper. Good old back titration. This should have been fairly straightforward in that it was in a familiar context. This is the back titration of aspirin, which is often the sort of exemplar that's used to teach back titration calculations anyway. It's nice and segmented for us. It's not all open. It asks us in multiple parts, so you can earn individual marks, even if you don't know how to work through the full process. But you should, because it's not that difficult once we break it down into individual components anyway. I would argue actually that the most difficult mark to achieve here is part A, just simply explaining what a back titration is, often ignored when you're focusing heavily on how to carry out a calculation. So here I was looking for something along these lines. Firstly, You could have said it's when an excess reagent is added to an analyte, and the excess reagent is then titrated with a second reagent. Simply saying that is fine. You got to say that at least. Some other variations: a tablet is added to excess sodium hydroxide. The titration shows the volume of sodium hydroxide left unreacted by the tablet. Or a known quantity of either an acid or base is reacted with an unknown quantity of some chemical. How much leftover acid or base remaining can be determined via titration, and so how much of it reacted with the other chemical originally can be worked out to determine the chemical's concentration. That third answer, and I would run that back to hear me say it again, is probably the preferred answer because it's a bit more open, a bit more generic. There's nothing stopping you referencing particular chemicals in the question, but I would keep it open. I should say in the guidance here it says back titration is used when one of the substances used is insoluble. In the case the aspirin tablet is insoluble, therefore back titration is not acceptable because you're not discussing the idea of excess. Simply stating that it's appropriate for use when one of your things is insoluble is a justification to carry one out, but it is not explaining what a back titration actually is. It's just the justification for carrying it out in the first place. So saying it's when you have something that's insoluble and you do a titration isn't really explaining it, it's just stating why you did it. So that's not the answer. B part 1, calculate the number of moles of sulfuric acid and the average titer. So for this one, what we're going to do is run a very simple calculation actually. We're going to look at an average volume used, and we're going to use that to do an NCV. Because if you think about it, in a back titration, we always want to start with our second equation, so we're starting here. If we want to figure out information about this here, we're looking to see when that was used. So the resulting mixture from the first process was allowed to cool, blah, 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 transferred to a flask, 25 centimetres cubed of that flask, a sample of that flask, were titrated with this concentration of sulfuric acid. The results are shown below. So clearly these are for the sulfuric acid. These are our average titers for that acid. So nice and simple, we can work out number of moles of hydrogen peroxide. Very good. It's been a long day. Number of moles of H2SO4 is C times V. Concentration is 0.05. Volume is the average between, let me see, these two here, because they're concordant. This one is not. It's also a rough titration, which you should generally avoid. Just quickly, that plus that divided by 2 is 8.65. We'll convert it to litres for the sake of time. So that's 0.00865. Be careful with your dividing by 1,000 there for that one. Just making sure you've got the right number of zeros. And then the final answer for that, 4.325 times 10 to the minus 4. That's our number of moles. Significant figure-wise here, really we should be going to 2, so 4.3, which this is a bit frustrating, but I would suggest that you give that answer there, and then if you want to be technically correct, you can quote a second answer, which does the rounding and the significance, so 4.3 in this case. But then, as you can clearly see, the next question is a carry-through question, so it needs us to use our values from the previous question. For this, I would like you to carry through the more accurate number, so that we don't lose accuracy in our final answer and our final rounding task. So calculate the number of moles of excess sodium hydroxide in the standard flask in this case then. What we need to do is, first of all, use our second balanced equation. So we've got this one here. We've figured out this number of moles, we want this one. So it's a 1:2 ratio. So I'm just going to write that out. So it's a 1:2 in the direction that we need it to go. Therefore, we have got 8.65 times 10 to the minus 4 moles in the sample that we used, and that was 25 centimetres cubed. Now we're wanting to figure it out for the standard flask, which was 250, so we're going to times that by 10. That's why we're working the scientific notation. So it's times 10 to the minus 3 moles in the 250 centimetre cube flask. answer we arrive at for part 2. For part 3, we have to calculate the number of moles of sodium hydroxide which reacted with the acetylsalicylic acid. So this one is where the wheels started to come off for a few people. So we leave this number behind for now, and we need to find out, first of all, originally, okay, what was the number of moles of any OH that we actually began the process with. So if we go back to the question, 5 aspirin tablets were crushed and added to 25 centimetres cubed of 1 mole per litre sodium hydroxide solution. This is the value that we want to subtract our excess number from, so that we find out how much was actually used in the first place. This is the kind of core of the back titration calculation process. So to figure out our initial, again it's C times V, it is 1 mole per litre times 25, so 0.025 litres. That's just 0.025 moles. So to figure out, let me just write this in plain English. To figure out the number of moles that reacted, I must take the original number of moles and from that subtract the excess used. Okay, so I have 0.025, and from that I'm going to subtract this value up here, the 8.65 times 10 to the minus 3, because ultimately that's what I had in the flask before I took a sample of it to do the titration. So that's what I had that hadn't reacted in my original reaction with the aspirin tablets. So if I take that away from what I started with, I'll have the amount that did react with the aspirin. And then from that, I can use a simple mole ratio to figure out how much aspirin I actually had, because that'll be how much actually reacted. So let's stop talking about it and just do it. 0.01635 moles is the answer for that section there. And that's an appropriate number of significant figures. Let me see. Well, I guess 0.016, I suppose. But we'll keep it as that, that's fine. 2 above, why not? Part 4, the mass of 1 mole of acetylsalicylic acid is 180 grams. Use this and your answer to part 3, which goes without saying if this was wrong, and you carried it through and used it correctly, you can still access both marks for this question. But we're using it to calculate the mass of acetylsalicylic acid in 1 aspirin tablet. So if we have a look at our mole ratio in the first equation here, it's 2 of these for every 1 of these. Now this here, because I don't want to draw that all out, I'm just going to call acetylsalicylic acid, just a short form version of the word. And as we can see from that equation, it's 2 to 1. So therefore, let's zoom in for this little bit, the number of moles of acetylsalicylic acid will be equal to this number of moles I worked out up here divided by 2. And I'm going to evidence that that's what I'm doing, because I'm starting a new calculation. So there we go. Just in case you make a mistake in the calculator and you've not evidenced where you've got that mistake from, it's good to show where you're bringing in a new number. Okay, so that's why I've written that little first part down there. So I've got the number of moles. That implies that the mass of acetylsalicylic acid is equal to that number, which is the number of moles, times 10 to the minus 3, multiplied by the GFM. Right, this is just a N times GFM calculation, which I should have written first, granted. If we do that and work that through, we find that it's 1.4715 grams. Now, that's 1 mark. This question is not worth 1 mark, it's worth 2. So it's expecting you to see the wood for the trees here, and it's saying the mass of 1 tablet. If we look back at the start of the question, it referenced clearly 5 aspirin tablets. So our value is inflated by a factor of 5. So therefore, the mass of 1 tablet is equal to 1.4715 divided by 5, which is 0.2943 grams. And if we're really going for accuracy and precision and all the rest of that good language, we really should be using 2 significant figures So approximately 0.29 grams